Hello, everyone. My name is Reece. I'm here to talk to you about the relativistic limits of white dwarf asteroseismology. Jumping right in, my research was inspired by data from the K2 and TESS satellites. These are both space-based satellite telescopes. Their intention is to measure transiting exoplanets in space. The way they do that is they look at some field of vision where there are stars, and they measure the brightness of light coming from the stars. And by seeing minute changes in that brightness, they can deduce the presence of exoplanets that are passing in front of the star, causing it to dim slightly. While it's looking at these stars, however, there's a lot of other objects it's looking at in its field of view. Among those objects are variable white dwarfs, which are the things I care about. For one of these variable white dwarfs, TESS or K2 will give us a light curve that looks like this. This shows the intensity of light from that white dwarf as a function of time. If we Fourier transform this, we get something like this, where you have these nice peaks at the normal modes of your light curve, showing the normal frequencies of variation. The broader these peaks, the more uncertainty you have about the star, meaning you don't quite know what the frequency is. The narrower the peak, the more certain you are about the frequency, and you have a more accurate measurement. With this Fourier transform, you can go through, find the centers of these peaks, and get a nice table of frequencies and periods for different modes inside the star. This is a cartoon picture, but for a real star, it looks something like this from the K2 data. And you can see for a lot of these modes in the Fourier transform, it has very, very narrow peak, meaning very accurate data. That's because K2 and TESS, being in space, are able to measure for a month at a time or even more these variable white dwarfs, getting very, very accurate data. This is what observers do. I am not an observer. I am actually a theorist. So for theorists, what our counterpart to this is asteroseismology. We begin with some model of a star. It solves a set of equilibrium equations, given astrophysical properties of it. And with this equilibrium model, we perturb it to first order to get a set of linear wave equations. Here they are in physical form. I can write them in slightly nicer form, so you can see it's a fourth order differential equation. I can write it a little bit better, and you can see it's an eigenvalue equation. Being an eigenvalue equation means that it has eigenvalues. Those are the predicted frequencies, what you predict to measure for this particular model of a star. You expect these to be the frequencies. If we have two different models with different internal physics, that'll lead to different pulsations and thereby a different set of predictions. So if we are able to match a model to the predicted frequencies of the model to the observed frequencies of the model, that allows us to constrain the internal physics of a star and kind of get a closer look at the inside of it. My question is, for white dwarfs, what if the only difference in these two models is whether I use Newtonian physics or Einstein's general relativity? For Newtonian physics, we have a pretty good idea how to do this. It's what everyone does in the field of asteroseismology for white dwarfs. For Einstein, however, general relativity has not been widely applied to white dwarfs. White dwarfs being what they are compact, but not overly compact. It suggests the post-Newtonian formalism as a way of treating this. To think of the post-Newtonian formalism, we often think of gravity as being Newtonian gravity, and then Einstein's general relativity is like a correction to Newtonian gravity. That is a backwards way of thinking it. General relativity is gravity. Newton is an approximation to Einstein's general relativity. So the better way of thinking of this is our two extremes aren't Newton and Einstein, but Minkowski and Einstein, where Minkowski's gravity is that there is no gravity. Newton then is one step closer to Einstein, an approximation to it, getting one step beyond Minkowski, closer to the full picture. Well, if Newton is one step beyond Minkowski, that suggests other steps beyond even Newton, which we call the post-Newtonian approximations. The first of them looks something like this. You get a set of equations that have a nice Newtonian form, but notice that there are more gravitational fields involved, indicating you're closer to Einstein's full picture. So I got a set of post-Newtonian calculations, made some models, calculated the pulsation here using post-Newtonian, and I was able to get a set of frequencies. And if I graph them here, I get this at long last. These are done for polytropes. I did polytropes so I could be isolating the effect of relativity and not worried about thermodynamics in the star. For a wide range of different models and for a wide range of different modes, you can see that the relative difference between post-Newtonian and Newtonian frequencies is at the expected order of the gravitational redshift of the white dwarf, and is also at the threshold where K2 and TESS could measure it. So that's all I have for you today, and thank you all very much.